4.4, applications of sinusoidal functions and their derivatives. So applications of sinusoidal functions is anything that's periodic. So tides coming in and out, pendulum, position of a pendulum, sound traveling, all those kinds of things, frequency, electricity. So we just have two examples that we're going to work through. One dealing with AC-DC circuit, so electricity traveling, and one dealing with a pendulum and its position and speed. Example 1. A power supply delivers a voltage signal that consists of an alternating current, AC, and a direct current component, DC, where T is time in seconds, the voltage in volts, at T time is given by the function V with respect to T equals 5 times the sine of T plus 12. A, find the maximum and minimum voltages and the time at which they occur. Max, min, voltages, and time they occur. All right, in order to do that, we are going to find our critical values by differentiating our given function. So we're going to calculate the derivative with respect to time, and then we'll set the derivative equal to 0 to find our critical values. So dv by dt, the derivative of v with respect to time, voltage with respect to time. Take the derivative of this first part and then the derivative of the second part. So common multiple rule, 5 stays out in front. Take the derivative of sine t, which is cosine t, plus the derivative of 12, which is 0. So we're just looking at 5 cos t. And we want to set that equal to 0 in order to find our critical values. I can divide both sides by 5. I just get cos of t equals 0. And so our critical values is anywhere that the cosine function crosses the x-axis. It's the zeros of our cosine function. If we want to think through that, we can draw it. Here's our cosine wave. Standard cosine wave. Again, I always find it easier to draw the wave and then draw the axes. It's kind of cheating, but it works. 1, -1. And then we have one full cycle. So right here would be 2 pi. Here would be pi. And then we need to think about where it actually crosses the x-axis. And that's going to happen right in between pi and 0. So one of them is pi over 2. And the next one is 1, 2, 3 pi over 2. And that continues, keeps on going. 1 pi over 2, 3 pi over 2. What do you think the next one's going to be? 5 pi over 2, 7 pi over 2. And that's going to keep on going and going and going and going. So there's actually an infinite number of critical values. But we can note here that the zeros occur at, and then we're just going to have a long set of them. By the way, they're going to be negative values as well. So you can come this way to negative pi over 2 and negative 3 pi over 2. So we're looking at an infinite number of negative zeros until we get to the zeros that we actually drew. Negative 3 pi over 2, negative pi over 2, working our way into the positives, pi over 2, 3 pi over 2, 5 pi over 2, and then it keeps on going infinitely and the ellipses there, the dot dot dot, indicates that we're going all the way to negative infinity by multiples of these terms, and all the way to positive infinity by multiples of this term. So we really need to generalize. We need to generalize this. You can't just write an infinite set. So if we wanted to represent all of these zeros algebraically, I'm going to give you, I think I'm going to give you a second. So these are all values of t at which zeros occur. So see if you can come up with a statement using.
Are we allowed to use modulus? Like say x mod 3 pi over 2 equals 0 or pi over 2 equals 0?
You can do it that way, but then also try to do it in the way that we've actually done it in functions class. So we're looking for t is the set of real numbers, and such that t is what? What constitutes t? And actually we don't probably need t as the set of real numbers. You just need t equals, and then some kind of general algebraic statement that includes all of these values. I'll give you a second to do that before I write it. All right, using set notation, t is equal to, we needed to create an only odd values in front of our pi. So we've got 2, and I'm going to use the letter n, 2n plus 1. That will give us all of the odd numbers, infinite negative and infinite positive. And then we're multiplying that by pi over 2. You could write it this way as well. You could write 2n plus 1 times pi and the whole thing over 2. That's fair as well. And we should note here that with n we're talking about integers. So n comes from the set of integers. That's positive or negative whole numbers including 0. Close it off. Lovely. Okay, now to determine whether or not these points are maximums or minimums, we're just going to inspect the graph. We're going to inspect the graph, and we're going to look at the slope at these points. So at the point pi over 2, we have a 0, we have a critical point. So right now it's a 0 of the tangent curve. You have to remember the thing that's graphed here is the derivative function, not the actual function. So where there's a 0 on the derivative function, there's a max or a min on the actual function v with respect to t. So when we're looking at this 0, we're talking about the red curve represents the slope of the original. So here the slope is positive because the tangent is above 0. Sorry, the derivative function is above 0. And on this side of pi over 2, the slope of the function is negative because our derivative function is negative. So if your slope is positive, and then negative, what type of critical point do you have? You have a max. So you have a maximum at pi over 2. Well, what about at pi over 3, 3 pi over 2? We go from left to right, we go from having a negative slope to having a positive slope. So at 3 pi over 2, we're going negative and changing to positive. So at 3 pi over 2, we have a minimum. And we can do that just by looking at the graph. So we're just going to identify a few of these, and then we can develop, we'll see if we develop a general equation. But, or you could test the second derivative at each of these points. But anyway, we'll just make a note at t equals pi over 2, we have positive to negative, concave down, that is a max. At t equals 3 pi over 2, we have slope negative changing to positive, that's concave up, that is a min. And we want to find the actual critical points. We're going to find the maximum and minimum voltages. So we don't actually have to test all of them, right? It's repeating. So we just have to test one max and one min. find the critical value, find the actual voltage at those points, and the time at which they occur. So we have at pi over 2, we want to find the value, the voltage, with respect to time of the original function. So we're subbing in pi over 2 into our original function, 5 times the sine of pi over 2 plus 12. And I'm just going to work, well, I guess I'll work down. There's some space still. Okay, what's the sine of pi over 2? Sine of 90 degrees. This is reaching back, isn't it? You could just chuck it in your calculator, or we could analyze the curve. And maybe I'll just do it down here. So right here is pi over 2 on the sine curve, and has a max of 1, and that's where it hits its max. So the sine of pi over 2 is 1. You could also think about your unit circle. Sine is the y coordinate of the point that intersects the unit circle. So if sine is the y coordinate, then it's 1. 0, 1 is the coordinate of this point. So the sine of pi over 2 is 1. Okay, so we have 5 times 1 plus 12, which equals 17. So the maximum critical value is 17. Okay, same process to find the minimum. Our original equation, sub in 3 pi over 2. We get 5 times the sine of 3 pi over 2 plus 12. And we're pretty aware that we're going to be down at our minimum here, which is going to be negative 1. And so we have 5 times negative 1, that's negative 5, plus 12, that is 7. And the maxima and minima alternate. So we could talk about all of the times at which these occur is the same as all of the critical values, but now we need to skip every other one of these. So if we're talking specifically about maximum, max values of 17 and where they occur, and then the minimum values of 7 where they occur, they alternate on this set. So I'll give you a couple seconds to think about how to skip every other one of these odd numbers now. David Gorobchuk, the brilliant one, realized that we're not just going up by 4 in the numerator. That's kind of a silly way of doing it. We're going up 2 pi. We're going 1 full period length. So we're starting at pi over 2, and then we're adding multiples of 2 pi, full period lengths, to repeat and repeat to get to from one max to our next max to our next max. Thank you very much. That's helpful. Where n comes from the set of integers, positive and negative numbers, including 0. Okay, so this one's going to be similar because they're also going to repeat every period length. But instead of starting at pi over 2, we're going to start at 3 pi over 2. So t equals 3 pi over 2 plus 2n pi. And you could, it maybe makes more, might be helpful for your brain to write 2 pi n. I'm not sure why they put the variable in between two values, but Anyway, that also comes from the set of integers. And this is our answers for time. So this is in seconds. Seconds. And again, these are the times at which the maximum values occur, and these are the times at which the minimum value occurs, repeated. One thing you have to be careful with when we're doing this is remember that we started with an original function, but we ended up graphing the derivative function and getting all our information from the derivative function, but we're actually talking about the original function here when we're stating things like the maximum and minimum values at these times. These are the zeros of the derivative function, and the second derivative would tell us whether they're max or mins, but when we write our answer, we're actually talking about our original function, voltage with respect to time. So be careful. Okay, in example 1b, we're going to determine the period t in seconds. Period t in seconds, which we've already done. The frequency f in hertz, and amplitude A, which is measured in volts for this signal. So kind of understanding what some of those things are. Again, we said we already did the period t in seconds. The period was 2 pi seconds because we didn't have a horizontal stretch or compression on the sine function. So we have period length t equals 2 pi seconds. The frequency is the reciprocal of the period. The frequency is the reciprocal of the period. So f equals 1 over t, which is 1 over 2 pi, or 1/2 pi, and that's measured in hertz, which is capital H. Z. And the amplitude of a sinusoidal function is half the difference between the max and min values. And we know how to get it straight from the equation. There's a multiplier, an a of 5 out in front of the sine t. So we know it's going to end up being 5, but in order to do it algebraically, the amplitude is 1/2 the voltage max minus the voltage min, the difference between the max and the min. So that's 1/2. Our max was 12, our max was 17, our min was 7. So 17 minus 7 is 10, half of that is 5. So the amplitude is 5 volts, which is also, again, the coefficient of the sine t term in our original equation. Okay, example 2, we are looking at a pendulum. So we basically have a ball swinging back and forth. And we're ignoring friction. So this is simple harmonic motion. We have a rest position, and it moves this way, and then it comes all the way back across. And it can be modeled by a sinusoidal function with constant amplitude. So it's gonna keep on going. It's never going to stop. The period of the simple pendulum depends only on its length and can be found using the relation t equals 2 pi radical L over G, where t is the period length. T is period length. So how long it takes, the time it takes for it to get from its rest all the way over to the right, all the way over to the left, and then back to its rest. Or from its right, all the way across, and all the way back, depending on where you start from. L is the length of the pendulum. L is the length of the pendulum. Should be right here. It's measured in meters. T, the period length, is in seconds. G is acceleration due to gravity. Which has a constant value of 9.8 meters per second squared on Earth. Okay, so under these conditions, the horizontal position, left to right, of this ball hanging from a pendulum on a string or rope with length L can be represented by horizontal distance with respect to time is equal to A times the cosine of 2 pi t over capital T. So all this stuff is given in the problem itself. I'm not doing anything new. I'm just recording what's in the problem, where A is the amplitude of the pendulum, which is amplitude, right, is half the distance between the max and the min. So this arrow that I've drawn from here, maybe I'll redraw it to here, that's A. You have that picture. And T is time in seconds, and capital T is the period length measured in seconds. And we are going to find the maximum speed of the bob and the time at which that speed first occurs. So find max speed and time it occurs. Let's talk about it first, because it's really not that difficult to understand it as a concept. If you're starting here and you're pulling the pendulum here and then you let it go, you're going to get a speed of 0 at 2 points. You're going to get a speed of 0 here, where it changes direction to go back, and a speed of 0 here. Okay, so then if those are our zeros, where is it moving the fastest? It's going to be moving the fastest when it's on its way down, right before it starts moving up again, because now gravity is pulling it back down on this side. So it's going to be slowing down to 0. Then it'll be 0, and it'll be speeding up, speeding up, speeding up, speeding up. And then it'll start slowing down to 0. Yeah, we get that? Okay.
Well, that would be the derivative of it. That wouldn't be the actual function's value.
So this will give the position, the horizontal position,
Yeah.
and the derivative will tell us the speed.
Yeah. Oh, okay.
So yeah, the zeros of the derivative, no, the max and min of the derivative will tell us where it's moving fastest, if that makes sense. So here we go. First, we're going to take this function that they've given us, and we're going to find its period length. So period is t, and we already have the function for t. T is 2 pi radical L over G. And we can sub in what we know. The last line of the problem tells us that the pendulum, in this case, has a length of 1 meter. Length of 1 meter, and amplitude of 5 centimeters. So its horizontal distance is given in centimeters, and its length is given in meters, so we're going to be careful about that. So all we need to do here is sub in what we know in order to get our period length, which we then can use in our formula. So basically what we're saying is this is a general formula for period length of a pendulum, not including friction. And this is our specific situation that we are in. So period length equals 2 pi radical 1 over 9.8. And we'll click that away in our calculator. And you get approximately 2.0. So the period length of our pendulum is approximately 2.0 seconds, which means for it to get from its rest position all the way to the right, all the way to the left, and back to its rest is 2 seconds. Or to go from a max all the way to its next zero and back again, 2 seconds. Now that we have that, we can sub it into our equation for h of t. And so h of t we have right here is a, which we know is 5 centimeters, times the cosine of 2 pi t in the numerator over our period length, which we said was 2 seconds. 2 in the numerator and the denominator cancel out, so we can reduce this to 5 times the cosine of pi t. So what is the derivative of a position function? We've done this before, so we had displacement with respect to time. That's what this is. What function is the derivative of the displacement function?
The speed function.
More specifically,
Velocity.
Velocity.
And then after that, we have acceleration.
And then you have acceleration. Okay, so that's what we're looking at. We're going to take this displacement function and we're going to find its derivative, which is going to give us the velocity at any point along the pendulum swing. And I think I have enough space here, so I'm going to do one more. So I'm going to write it in 2 different ways. We'll write velocity function is equal to dh by dt, so the derivative of our horizontal displacement function. And I'm just going to keep working. I can work down. And the derivative of this guy right here. What is the derivative of a cosine function?
Negative sign.
Negative sine function. So we're going to end up with, and then we take the derivative of the inside as well, right? I'll do it separately. So we're looking at, I'll do it all separately. 5 times negative sine pi t times the derivative of the inside, which is pi. Remembering pi is just a number, right? So this is a number times t to the power of 1. So our variable will drop to t to the power of 0, and we're just left with our constant. We can reduce this guy. I'm going to bring this negative out in front of all of it, and I'm going to bring pi out in front of all of it because multiplication is commutative. Negative 5 pi times the sine of pi t. That's now our derivative function, which gives us the velocity, which is the speed of the pendulum at any point. Okay, we're going to find the max speed. That will happen at the zeros here. But before, actually we don't, so if I find the zeros now, I'll get the max and the min. I'll get all the critical values. I don't want that. We're just looking for the maximum speed. So what we're going to do is, we're not going to graph it. Last time we graphed and we analyzed the graph to get our answer. This time we're just going to take the second derivative. So we're actually going to get the acceleration function with respect to time. So again, the second derivative of this thing, we've got negative 5 pi out front. I'm just going to bracket that to keep it organized. The derivative of sine is cosine. So we have the cosine of pi t. And then we're going to multiply by the derivative of the inside here, which is pi. So if we reduce this, I have 2 factors of pi. So we have negative 5 pi squared times the cosine of pi t. You don't actually really need these brackets because pi is just a number. You could just write this, and it means the same thing. But I find it's easier, especially if I'm going to write another variable there, multiply it by that. Okay, so now the maximum of this function. Okay, so now we're looking for this function. I'll draw it. The original function goes up and down. Okay, d of t goes up and down, and its maximum speeds occur at the zeros of this function, of our second function, v of t. But we don't know if these are max or mins. Okay, well, the max, no, I'm saying it wrong. We already found out that the maximum our maximum velocity will occur, our critical points for velocity will occur where our acceleration function is equal to 0. This velocity is positive, moving one direction, and negative, moving the other direction. But because we're looking for speed, find the max speed, not velocity, we don't care which direction it's heading. So every time it hits this point, we know we're going to be at a maximum speed. But we did that just through analyzing and looking at it. To do it algebraically, we're going to find the zeros of the second derivative function. So that's what we're going to do now. So find the maximum speed by setting the second derivative equal to 0. Which is to say where cos of pi t equals 0. Anything times 0 is 0, and this part can't be 0. So when is the cosine function 0? Cos is the x's. So the first time that cosine reaches 0 is at pi over 2. So pi times t has to be equal to pi over 2. So this occurs where pi t equals pi over 2. Pi over 2 is pi times 1/2. So t equals 1/2. Pi times 1/2 is pi over 2. Since we're talking about seconds, we'll put it in as a decimal. That's 0.5 seconds. So the maximum speed occurs, if you pull this thing up and you let it go, the maximum speed will occur at 0.5 seconds. And after 1 second, it will stop and come back. And after another 0.5, so 1.5 seconds, it'll be at its max speed again. And then 2 seconds, it'll be at a speed of 0, and it will have completed 1 period length. So that's a whole lot of trigonometric and algebra and calculus work for very little gain, because we knew that already. If you start your pendulum and it has a period length of 2 seconds, then you're going to have 1 second a stop and 1.5 seconds your full speed again, and 0.5 seconds your full speed. And anyway, so this is where it first occurs. Then to find out what that speed actually is, we're looking at our velocity function. So we're looking for v of 0.5 or v of 1/2. Sub that in, we get negative 5 pi times the sine of 0.5 t. Click that away in your calculator. Actually, you don't even need your calculator. You get, if we reduce this, this is the sine of, and this isn't 0.5 t, this is 0.5 pi, because it was pi t or t pi. 0.5, which is pi over 2. The sine of pi over 2 is 1. So we have negative 5 pi times 1, which is just negative 5 pi, which is approximately negative 15.7. Now that's velocity, and we're just looking for speed. Speed does not take into account direction. So we have now figured out that the max speed, therefore max speed of pendulum is 15.7 centimeters. Horizontal distance is given in centimeters. Centimeters per second. And this occurs at first, it occurs at 0.5 seconds. Maybe put the word first. You have a picture of a graph on the handout that I gave you. So this isn't necessarily reality, right? Because what exists in real life? This pendulum is not going to keep doing this indefinitely.
There's a air resistance.
Yeah, there's at least a little bit of friction between the air or somewhere up here. Okay, so this actually slows down into what's called dampened harmonic motion. So it's going to start looking like that, but it's actually going to be a combined function that ends up looking something like that, starting from here. So that's cool. Okay. Again, really helpful to just think through the problem while you're doing it. And then it's the concepts are pretty straightforward. And then keeping track of your first derivative, second derivatives, things like that. Draw your unit circle when you need to. Draw the sine cosine functions when you need to. And practice problems come from page 241. Numbers 1 through 10.